Section 5.5, Substitution. We have a theorem here, integration by U substitution. So let U equal g of x, where g prime of x is continuous over an interval, and let f of x be continuous over the corresponding range of g, and let cap f of x be equal to an antiderivative of f of x. Again, we will likely choose a c value if we were working with a definite integral. However, if we were working with an indefinite integral, then we actually have to include our plus c. Then f of g of x times g prime of x dx equals f of u du, which equals cap f of that function u of x, plus c, and then we plug back in what the value of u is. So let's go ahead and just apply this very quickly. What we want to do is choose a value of u equal to some composite function. If you have something that is being evaluated, something that two functions composed, that's always a good choice. So an inside function. So I'm looking at this and noticing that is raised to the fourth. Let's go ahead and say u equals 3x squared plus 4. Now, I need to replace the dx with something. So I'm going to say du, that's the derivative of this with respect to x, is going to be 6x dx. So I'm going to use du to replace the 6x dx. So I'm going to have my du there is taking place of dx and the 6x. And then I'm going to put down u to the fourth. And that is taking place of that right there. I have taken care of everything. These are actually the same integral with that substitution of u equals 3x squared plus 4. But I can take the integral of u to the fourth much easier. The antiderivative is u to the fifth over 5 plus c. Then I'm going to replace back in what my value of u is once I've taken the antiderivative. So this is 3x squared plus 4 to the fifth over 5 plus c. The idea is actually to make our lives quite a bit easier. So again, look for an inside function. This is really the chain rule in reverse, okay? But we're looking for the inside function still. Find an antiderivative of the integral of z square root of z squared minus 5. My inside function here, my choice of u is going to be z squared minus 5. Then that means du equals 2z dz. And I do want to write this up clearly so that someone else could follow it. Okay, now this is not exactly what we want, because what I would like to replace is a z dz, not a 2z dz. Alright, so that is true. Or I could say 1/2 du equals z dz. So going up here, that is going to be 1/2. There's the 1/2 factor. Put my du. And then that would be u to the 1/2. Taking the antiderivative, 3 over 2, and that would be 2/3. Alright, plus c. Now I cannot forget my factor of 1/2 that was out there. So that is going to be 1/3. I'm going to go ahead and substitute back in my u. Z squared minus 5 to the 3/2 plus c. All right, that is my antiderivative. Example 3. Find an antiderivative of sine t over cosine cubed t. Okay. My inside function here is going to be a cosine because I have that cosine cubed. Now we know that sine and cosine are derivatives of each other, disregarding a constant there. So it really might seem like you might want to choose sine. But we have to be careful because this cosine is cubed, so we want to choose it to be as our inside function. We want to choose that. Okay, then du equals sine t dt, which means my sine t dt is going to be absorbed by my du. That is 1 over u cubed. I'm going to go ahead and write that as u to the negative 3. All right, so the antiderivative of that would be negative 2. That would be taking the derivative to be negative 4. Negative 2 divided by negative 2, so we'll make that negative 1/2 plus c. And then to substitute back in, negative 1 over 2 cosine squared t plus c. All right, example 4. Find an antiderivative of x divided by square root of x minus 1. All right, let's begin. Let u equal, and it looks like the inside function there is x minus 1. Then du equals dx, that would just be 1 dx. This leads to a small problem because we can't actually replace the x there. We have x dx, not just we can't just say x du because then we have x's and not u's. So what we're going to have to do, okay, we're going to say this, du equals dx and x equals u plus 1. And this is coming from that statement right there. So this can be written as the integral of u plus 1 over the square root of u du. Alright, well, that is u to the 1/2 plus u to the negative 1/2. The antiderivative there would be u to the 3/2 divided by 3/2, so times 2/3, plus u to the 1/2 divided by 1/2, which is 2. Okay. Okay, good. Plus c. Now, evaluating that back for our value of u, which was x minus 1. X minus 1 to the 3/2 plus 2. X minus 1 to the 1/2 plus c. Always make sure you to get back into terms of x. That is very important. All right, definite integration with U substitution. This will actually work out exactly the same, except we are going to change our limits. So they begin as a and b, but once we make our substitution, we're going to change these to g of a and g of b. I'll show you how to do that very quickly, all right, as we look at our next example. All right, so finding the antiderivative is going to work out the same as it did previously. We will say let u equal 1 plus 2x cubed. That's a good choice. Let's make that a little clearer. Okay, then du equals 6x squared dx. That's sort of close. We actually want just an x squared. So let's say 1/6 du, or 1/6 du equals x squared dx. All right, also, I'm going to go ahead and write it out this way. Okay, our a equals 0, and actually let's just draw a chart. I'm not going to explain this one. Let's go from our x values, our limits a and b. We want to find out what those values are under u. So my endpoints were 0 and 1. If I evaluate those into my u function here, if I plug in 1 here, I get 3. So my new endpoint is going to be 3, my upper endpoint, my upper limit of integration. If I evaluate this at 0, I get 1. So what I'm going to do is have an integral from 1 to 3 of 1/6, I'll put that in there, 1/6 du, and that is u to the 5th. One benefit to changing the limits is that I actually don't have to go back in terms of x. I can deal completely in u now. So this would be u to the 6th over 6, evaluated from 1 to 3, and I'll keep my 1/6 in there. And that should be 182 over 9. I can just evaluate those two endpoints and I'm done. I don't have to go back in terms of x because I changed those limits from limits in x to limits in u. All right, example 6. Evaluate this integral. All right, well, it looks like our composed function here is 4x squared plus 3. That means our du is 8x dx. However, we want to substitute in an x dx, so we'll modify this by a factor of 8. 1/8 du equals x dx. Okay, and I've got my x endpoints, and I want to convert those to u. So those are 0 to 1. Evaluating that in there, I get 7. And evaluating at 0, I get 3. So I'm going to take the integral from 3 to 7 of 1/8, I'll go ahead and factor that out, du, and that is e to the u. Alright, well, that will be e to the u. It's the only function that is its own antiderivative. Alright, so this will be 1/8 of e to the 7 minus e to the 3rd. Just go ahead and leave it like that. And that will be approximately 134.568. Let's go ahead and box all of that in. All right, one last example with this. This one has a small trick that turns out to be very handy later on in calculus. Evaluate integral from 0 to pi over 2 of cosine squared theta d theta. Alright, there is a trig identity, and this is what comes in handy. Cosine squared theta equals 1 over, okay, so this is going to be 1 plus cosine of 2 theta over 2, which is equal to 1/2 plus 1/2 cosine 2 theta. So what this becomes is the integral from 0 to pi over 2 of 1/2 plus 1/2 cosine 2 theta d theta. Let's put this in brackets. Okay. Okay, well, the first part, I'm going to treat this as two integrals, actually. I'm going to break this up because I can do that. Plus 1/2, integral from 0 to pi over 2, cosine 2 theta d theta. For the first one, it's going to be fairly straightforward. That's going to be 1/2 theta, evaluated from 0 to pi over 2, which will be pi over 4. Alright, so the first bit is pretty straightforward. For the second, we want to let u equal 2 theta, which means du is 2 d theta, or 1/2 du equals d theta. So this actually gets a U substitution. We get a U substitution there. So this is going to be the integral. I'll leave the 1/2 constant there. Cosine U du. Now my limits are going to go from 0, and these are thetas, to my U values, from 0 to pi over 2. Okay, evaluating that into 2 theta, okay, that is going to be pi and 0. So the integral from 0 to pi of cosine U. And notice we had to put in a 1/2, so actually there should be another 1/2 coefficient there. So this is 1/4, and this is sine U evaluated 0 to pi. Well, at 0 and pi, sine is 0. So this is pi over 4 plus 0, which is just pi over 4. And that brings us to the end of this section on U substitution.